Welcome to this explainer. Today, we're diving into something we all literally look right past every single day. We're talking about glass. It is an intensely hot, highly precise industrial marvel. We're going to see exactly how humble, rough, completely opaque sand gets transformed into the perfectly flat, totally invisible material that literally shapes our modern world. Seriously, it's a wild question, right? How does something as coarse and grainy as a handful of beach sand become a flawlessly clear skyscraper window? Well, the answer involves a massive, continuous baking process. It combines extreme chemistry with a scale of engineering that, honestly, is absolutely gonna drop your jaw. So, to wrap our heads around this, we're gonna follow the actual journey of a sheet of glass straight down the manufacturing pipeline. We'll start with the ultimate glass recipe, turn up the heat in the furnace, look at the float glass revolution, walk through the annealing and cooling process, and finally, check out how they cut and package the final product. All right, step one, the ultimate glass recipe, mixing the raw materials. Our journey kicks off in what's known as the batch house. This is where the glass recipe is carefully weighed, mixed up, and prepped long before it ever sees a flame. You know, just like baking a cake, making glass needs a super precise chemical recipe. The foundation, roughly 50% silica sand. Then, manufacturers add in soda ash, limestone, rouge, and dolomite. When you mix all that together, you get what's called soda-lime glass. And this specific chemical balance is incredibly important, mostly because soda-lime glass makes up about 90% of all modern manufactured glass out there. We're talking everything from your kitchen drinking glasses to giant commercial windows. But wait, there's a secret ingredient to this recipe, and it's called cullet. Now, cullet is basically just recycled scrap glass. Manufacturers usually whip up a blend of about 80% raw mixture and 20% cullet. And why do they do that? Well, it's not just to go green and reduce waste. Adding cullet actually makes the melting process way easier. To put it in perspective, for every 10% of cullet they add to the batch, the factory saves about 2% in energy costs. So yeah, it's a massive efficiency win right off the bat. Moving on to step two, turning up the heat in the melting furnace. Once our ingredients are perfectly mixed in those giant agitators, we leave the batch house and step right into the roaring, violent heat of the continuous melting furnace. Now, the absolutely crucial thing here is getting the temperature just right. And by just right, I mean a mind-boggling 2,900 degrees Fahrenheit. That's right around 1,600 degrees Celsius. At this extreme, insane temperature, the solid sand, the rock, the recycled cullet, it's all completely melted down into this glowing, super viscous liquid. Seeing the raw materials cascade directly into that blazing furnace is just wild. The sheer scale of these operations is hard to wrap your head around. These are continuous glass melting furnaces, which means they literally never shut down. They run 24/7, all year long, sometimes for up to 16 years before they even need a rebuild. A single one of these beasts can process up to 1,000 tons of glowing, molten glass every single day. Just think about that volume. Okay, step three, the float glass revolution, how glass actually gets flat. We've got our molten liquid, but now we hit a massive historical roadblock. For a long time, the biggest headache for glassmakers was figuring out how to take this thick, molten syrup and make it perfectly flat without spending an absolute fortune on polishing or ending up with warped windows that totally distort your view. See, back in the day, the old sheet glass process involved pulling the glass vertically. It was cheap, sure, but it gave you inconsistent thickness and terrible optical distortion. To fix that, they came up with plate glass, where they rolled it horizontally and then physically ground and polished it flat. Great quality, but crazy expensive. The brilliant, game-changing solution finally arrived in 1959. It's called the Pilkington float glass process. It completely flipped global glass production on its head by delivering perfectly flat glass at a super low manufacturing cost. So let's break down how this ingenious process actually works. First, the molten glass leaves the furnace and cools just a bit, down to about 2,200 degrees Fahrenheit, as it flows over a refractory spout. And here's where the magic happens. It gets poured directly onto a bath of molten liquid tin. Because the liquid glass is less dense than the liquid tin, it doesn't sink. Nope, it just floats. Thanks to gravity and the natural surface tension of the tin underneath it, the glass naturally spreads out into this flawlessly flat, perfectly even ribbon. Zero mechanical grinding required. It's brilliant. And what's really cool is just how versatile this float process is. Your standard clear float glass naturally has a bit of a green tint at the edges, and that's just because of the iron content in the sand. But if manufacturers tweak that initial batch recipe, specifically by cutting down the iron oxide, they can create low iron glass for those ultra-clear, pristine, frameless edges you see in high-end buildings. They can even toss in metal oxides like cobalt or copper right into the batch to create beautifully tinted blue glass.
Now, as a quick aside, while the float process is absolutely the king for making massive architectural windows, it's pretty fascinating to note that the same molten liquid can be shaped in totally different ways for other applications. You've got the ancient manual art of glass blowing, where you literally inflate a bubble of glass on a pipe. Then, on the complete opposite end of the high-tech spectrum, you have Corning's fusion draw process. They use this highly automated proprietary isopipe where the glass actually overflows and fuses at the bottom. That's how they make the continuous, microns-thin, perfectly pristine cover glass that's sitting on your smartphone right now, completely untouched by human hands. All right, back to our factory floor for step 4, annealing and cooling down in the layer. So we have our massive sheet of flat float glass. It's perfectly flat, but now we're facing a brand new danger. And that is thermal stress. If this red-hot glass cools down too fast, or even just unevenly in the open air, the internal stress will literally cause it to violently shatter into thousands of pieces.
To stop that shattering from happening, the glass has to follow a super strict temperature timeline. It hits the tin bath at around 2,000 degrees Fahrenheit. By the time it makes it to the end of that bath, it's solidified into a ribbon at about 1,100 degrees. From there, it enters a highly specialized controlled cooling tunnel called an annealing layer. This tunnel's entire job is to slowly, uniformly bring the temperature down to a nice, safe 125 degrees Fahrenheit. This carefully releases all that internal mechanical stress before the glass ever hits normal room temperature.
And finally, step 5, cutting the final product, which involves inspection and packaging. Once the glass survives the annealing layer, we've finally reached the end of the production line. And just to give you a real sense of the scale here, we are now roughly half a kilometer, so about a third of a mile, away from where that raw sand first entered the melting furnace. It's a huge operation. At this final stage, it's all about perfection. The pristine, solid glass ribbon glides under these highly automated laser and camera inspection systems. These scanners are hunting for any tiny bubbles, inclusions, or blemishes. If they spot a defect, boom, that section of glass is automatically cut right out. And remember our secret ingredient from earlier? Yep, that defective glass is immediately recycled and sent straight back to the batch house as cullet. The system also trims the edges of the ribbon just to shave off any mechanical marks left over from the floating process. What makes it past those scanners is absolutely flawless glass. It then gets sliced into customer-specific sizes. We're talking massive jumbo sheets that can be as large as 130 by 240 inches. Before they pack them up, these giant sheets get lightly sprayed with a specialized separation powder that just makes sure that individual sheets don't stick together and keeps them from scratching each other when they're stacked, stored, and eventually shipped off to construction sites all over the world. So looking back at this whole incredible journey, it really does leave you wondering, doesn't it? How does a material born from such an intense, chaotic, and volcanic alchemy of raw dirt and extreme heat produce the flawless, invisible shield that quietly frames our daily lives? The transition from opaque grains of rough sand to perfect transparency is honestly nothing short of industrial magic. I really hope this explainer has illuminated the hidden complexity of this everyday material for you, and that maybe, just maybe, you'll never look through a window the exact same way again.